Okay, I want to talk about high accuracy camera calibration and why this is important. Every year it is more important to have precise structure from motion and precise depth recovery from stereo cameras, and especially for short-range stereo cameras, for example, for future mobile phones and so on. And the calibration of these devices become some bottleneck of the accuracy of the other tasks. Probably most of you is familiar with common approach in camera calibration. It's working simple. We just taking photos of planar calibration targets, detecting individual features, for example, corners or circles or something other, and then running some bundle adjustment. It's a Gauss-Newton optimization of camera calibration parameters and extrinsic of the calibration pattern to the camera. Positions and rotations of the camera. You can find this approach in OpenCV, MATLAB, and many others computer vision libraries. Okay, what's wrong with this method? First of all, if you calibrate camera, you often get just unreliable results. For example, very different focal length and different dimensions, and you get invalid uncertainty estimation. It's especially with OpenCV implementation and so on. And we have a very big reprojection error. The final error after bundle adjustment with modeled feature positions and observed feature positions. Okay, and the current bottleneck of this pipeline is a precise feature location inside this made photos. This is because detection procedure is working with very highly warped perspective warped and radial distortion warped image, and it's not too easy to handle all these warpings because it's very not linear warping. Okay, and the second big problem that errors of the feature location is systematic errors. So we have systematic distortion of the image, and we get systematic errors of feature locations, and then we have a large system error in the calibration parameters. Okay, we're starting to solve all these problems. We're using the common approach to camera calibration, but we're starting to solve all accuracy problems. The main problem, of course, it's feature location of the features with subpixel accuracy in observed images. And as I said, the main problem is distortion of these features. How we can handle all these distortions? There is a simple trick, call it frontal image or frontal parallel image, or maybe rectified image. We can run our calibration pipeline as usual and get some coarse estimation to the calibration parameters. And using these calibration parameters and camera projection parameters, we can rewarp back the warped image to the unwarped version. The frontal image is a parallel image to the camera plane. So the detection of the features stands very simple. We now not detecting some ellipses or curved corners or so on. We can detect exactly circles and exactly rectangular corners. Next one. How to precisely detect features in the image plane. We can use good known technique. It's a digital image correlation. It's very similar to the high precision optical flow. The common accuracy of these methods is about 1 millipixel. 1 millipixel. Just note it. For a block of pixels, about 20 to 20. No, highly textured blocks, 20 to 20 pixels. It's normal have millipixel precision. Okay. Sorry. Using this technique, we can detect our features with provided accuracy, about 1 millipixel, and we can use so-called circular features. Why? Why is this circular features? Because we don't want to estimate the rotation of our feature. We just can skip it and estimate only the position, localization of the feature in 2D. There is two common approaches to this. We can use model-based digital image correlation. What is it? If we know how our feature looks, we can model it, model its image, just render its image under given parameters and compare the rendered image to the observed one. And then we just can change our parameters to minimize error between observed and rendered feature, landmark. It's not very simple because real observed landmark have some brightness, contrast, have some blurring, have some non-linear luminance profile, and so on. And to properly fit this kind of feature, we should model all these noises. Okay. And there is a second approach for circular markers. It's a symmetric, central symmetric correlation. What we can do? We can correlate marker image with the mirrored image of itself, or transposed image of itself. Then the minimum error, we will get minimum error when markers is transposed or mirrored exactly through the center of the marker. And again, we can parameterize this center of the marker and change it to minimize error between these images, observed and mirrored observed. And in this case, we shouldn't model any brightness, contrast, and blurring, and so on, because it's almost same for all image. Okay. When we apply this digital image correlation to the feature location, we have excellent accuracy in marker locations, about 1 millipixel. And 1 millipixel in common conditions, it's about 1 micron, 1 micrometer, 1 micrometer. And here the bottleneck is an imperfection of our calibration pattern, because it's printed with reduced accuracy, and it's not really planar, because paper is distorted and computer monitor is distorted and so on. So we should compensate all these noises in our pipeline. How can we do it? In our bundle adjustment procedure, we can add not only positions of the cameras and calibration parameters. We can put the positions of the individual features and estimate not only ideal positions of features on the calibration pattern, but we estimate real positions with all real distortions, of the calibration pattern. Okay, after this procedure, our average precision of calibration can be about 5 to 10 millipixels. It's an average standard deviation. Okay, if you deal with bundle adjustment, Gauss-Newton optimizations, and so on, we not often deal with good optimization functions, with one global minima, and so on. So our next bottleneck will be numeric problems, numeric optimization problems. How can we solve this? Generally, we have no excellent ideal solution, but what we can do, we can change parameterization of calibration parameters of the camera extrinsic, of the point representation, and so on. We can use different cost function, not only a projection cost function, but angular cost function with not a Cartesian coordinate system, and so on. And for example, when optimization is stuck, we can iteratively change the representation, parameterization, and cost functions to continue minimize our error in different spaces. Parameterization and optimization of different parameters can be done easier. For example, some radial distortions much better optimized when we have not Cartesian but cylindric coordinates and cylindric errors in cylindric coordinate system. And the last one, what we want to get, it's estimate the uncertainty of our calibration. Many common packages provide this uncertainty, but it's completely wrong. So OpenCV report precision of focal length about 0.5%, but real precision, if we experiment and run it many times with different scene, will be about 20% and so on, with order of magnitude higher. So why this is happening? Because good known packages just taking the part of information matrix and without elimination and always the correlation and parameters, just taking its diagonal values to represent uncertainty. From math point of view, it's not correct. We should take all the information matrix and sequentially eliminate all correlated parameters from this. It's done simply by Schur complement and so on. And having the final matrix, information matrix with the calibration parameters, if we want to have individual uncertainty of every parameters, we should eliminate all others sequentially. Okay, and at least we will have a good calibration and good uncertainty estimation of this calibration. Okay, and what we can do further with our calibration, just note that calibration accuracy about 10 millipixels is good enough. It can be broken by just changing temperature of the camera sensor. It's comparable in accuracy with these values. But what we can do further? First, we can develop procedures that removes or compensate all errors from symmetric center correlation. We can develop different type of parameterization of calibration parameters, because direct optimization of calibration parameters as focal length and so on is not often good choice. We can develop new types of individual features that provide much more texture information for digital image correlation. And of course, if you develop some package and contribute it to MATLAB or OpenCV, I think your name will be very famous in computer vision industry. Okay, and if you want to read about all the stuff, you can read these 3 papers. It's, I think, enough. These 3 papers and, of course, connected publications. So, thank you very much. Maybe you have questions.
You have questions? You have a question.
1 millipixel accuracy seems very high. Why do you need such accuracy?
For example, it's very important for short-range stereo cameras. Short-range stereo cameras have baseline about several centimeters. And you want to get maximum accuracy for depth recovery. So accuracy can be too much for this task, for this kind of task.
How 1 millipixel in this case translates to depth in accuracy?
Oh, I can't answer you, but I don't know, maybe after presentation we can sit and calculate it.
What is the order of it?
No,
Yeah,
I can say it without calculations.
Is there exists standard databases or benchmarks to check your quality?
Yes, it exists. Just print your calibration pattern.
No, I mean standard test, standard benchmarks.
What do you mean standard?
I mean that some downloadable database, some zip archive that could be downloaded.
I don't know. There is some standard
something like NIST.
examples presented in these publications. You can use these calibration patterns and these images.
Okay, thank
for
you.
verification. Sorry?
Like a testing data set.
Yes, probably these publications have a lot of data sets with provided ground truth information.
Hi, wonderful talk. And I'd like to ask, in your work, do you have to calibrate the cameras with huge radial distortion, like very high field of view? Did you try it with your method?
Generally, me, just No, no. Personally, me was not deal with fisheye cameras and so on. I think with distortion, with cameras about 90 degrees field of view, not more. But I think this method works for every camera. It's flexible. You can change the calibration parameters model according to your real camera.
You mentioned dependence on the environment of the parameter of you estimate. You mentioned the temperature.
Yeah.
So my question, will you plan to extend your exploration, your research, to not use etalons in camera calibration? Because we can imagine, and there exists situation when you cannot exploit the etalons, but you can use the scene statistics. Thank you.
Yeah, I understand. First of all, it's not my research. It's all research of these guys. I just used these researchers in my work. Second, there is existing techniques to calibrate some stereo cameras, short-range stereo cameras in real time, but it's a different methods and different techniques. It's not described in this presentation.
Yes, but I asked about your plans.
Okay, it's under NDA, of course.
We have one question, another question, and Juan. Okay, so we have 3 questions, okay? Yeah.
Just a short question on the reduction of parameters used. You said what kind of techniques or methods do you use to reduce the number of parameters? You had it on one of the last slides.
It's called sure complement of working with information metrics. Sure complement, it's a mathematically correct elimination of correlated parameters.
Do you describe more details about difference between cylindric coordinate system and Cartesian coordinate system of the camera according to accuracy of the camera calibration? I mean, for example, for huge radial distortion, it's more suitable spherical coordinate system.
Yes, spherical coordinate system.
And you said about cylindrical coordinate system.
I just forgot how it sounds in English. Yes, spherical coordinate system.
But what is different in accuracy? In 2 words.
It's not difference in accuracy. It's different in сходимость. Господа, как сходимость? In convergency of optimization. Because in spherical coordinate systems, you have errors like first angle and second the magnitude of offset. Difference in magnitudes with these 2 vectors, and this magnitude is highly correlated to the radial distortion coefficients. No, because radial distortion coefficient is working in spherical coordinate systems. Just. Sorry. Personally, me, I don't have this information or research, and probably I've never used tangential distortions in my work. But of course, this pipeline can use very complicated models of camera.
We just had the first case when you used whiteboard for explanation, so I think, yeah.
My question is, how different are the cameras from the same manufacturer? So do we have to calibrate every unit?
Okay, I understand. We have to calibrate every camera.
So then how can it be done? Should it do the manufacturer of mobile device and calibrate its stereo camera, or every user can do it?
Yeah, many stereo cameras comes with already calibrated parameters, but I really didn't meet such kind quality of calibration, and of course taking the different cameras with from one manufacturer, the parameters can change about I think maybe up to the 5% of focal length of center of image and so on.
Thank you.
You can keep camera, change the temperature.
It is important only, I think, in close range stereo cameras, because in common application, it's not very important.
Okay, Michael, thank you very much for your presentation. Yeah.